Swayam Prabha. Digital India. Educated India.
Often teacher gets this complaint from students, sir, you are solving very simple problems and asking us difficult problems. So for a change I am going to try a little difficult problem, a problem that is usually unusual. So we are going to solve a beam problem using virtual work principle. Okay. So this is a beam problem. Say I need to find out the reactions at A, that is the problem given to me, okay. And we have to use virtual work principle. We can use other principles also. Mind you, in virtual work principle one of the advantages I will get is I will only have active forces participating as long as I have kinematically admissible displacements. The moment I have kinematically admissible displacements, it becomes easy, alright. So let us do that exercise to find out. I need to find out the reactions at A using virtual work principle, okay. What would be the first step? Okay, it is quite procedural and therefore we will start with each of the steps that we have to carry out. The first step that we have to carry out here is find out what kind of system it is. Is it a system with 1 degree of freedom, 0 degrees of freedom, 2 degrees of freedom? In other words, is it a stable beam, is it an unstable beam? Okay, it is a over stable beam, or in other words it is an indeterminate beam. Okay. So we need to find that out. To find the degrees of freedom for a beam we already know. Let us just have a recap. If I have a beam like this, at this point it is prevented from rotation as well as movement. Okay, it is a beam problem, which means horizontal displacement is redundant. Okay. So if I have apply a force here, is it going to be stable? That is the question I am asking. Okay, if it is stable, what is the degree of freedom I have? Is it positive 0, positive 1, 0 or negative? Each one of this will give me an idea of what this beam is. Well, okay, there are 2 degrees of freedom, forget about x, there are 2 degrees of freedom for this rigid body, okay. And if I have 2 constraints for this rigid body, that means total degrees of freedom is equal to 0, very simple. How many degrees of freedom do I have? I have 3 degrees of freedom for a rigid body. Since this is a beam, one of the displacements, the horizontal displacement, is a redundant, which means I will take it to be 2 degrees of freedom, y displacement and rotation. Okay. And how many constraints do I have? 2 constraints, which means that imposes 2 constraints to the degrees of freedom, which means I have a 0 degree of freedom system. 0 degree of freedom system means it is a stable system. Okay. You will not see any movement of this rigid body. If I have to see the movement, I either have to remove it completely. If I remove it completely, how many degrees of freedom I have? There are no constraints, which means it has 2 degrees of freedom. Supposing I instead put a hinge over here, this means I have not 2 but 1 constraint, which means I will get 1 degree of freedom. Supposing I do like this, please notice it carefully. I am going to release the vertical displacement, but will not allow rotation, which means what? It is rigidly connected to this guy, and this guy can slide only like this. So this guy cannot rotate like this, okay. So another way of drawing this is it has something like this, where rotation is not allowed, only vertical displacement. How many degrees of freedom will this have? Of course, the total degrees of freedom possible are 2. There is one constraint in terms of rotation, which means -1, I will get 1 degree of freedom system. Okay. So this is the simple idea. Now let us look at this particular beam which we need to solve. Okay. Now this beam consists of many things, so it is complex to look at to start with, right. Let us just break it down so that it is easy for us to understand. There is one part AB, so I am going to write AB, there is another part BC, another part CD. So I am breaking it down into the 3 rigid bodies which are connected through hinges, alright. Let us come back to this A later. Between AB and BC, what do I know? The displacement, supposing I fix AB, the displacement B of BC is fixed, alright. So it offers a constraint at B, whatever is the displacement of AB at B, it is the same displacement of B at BC, correct, and therefore can it rotate between them? The rotation between them is allowed, right. So as it is, we already know each one of them can have 2 degrees of freedom, so I am just writing that here. Okay. This is free degrees of freedom. It does not make sense, but let us just understand it this way. If I completely free it as a beam, which means horizontal displacement is redundant, 2 degrees of freedom possible for AB, BC and CD. For AB and BC together, there is one constraint that is offered at B, right. So I have a -1 between AB and BC. Between BC and CD, another constraint is in the form of hinges there, so one more is gone, alright. How about the support at F? It vertically constrains the motion. Support at G again vertically constrains the motion, which means one constraint each at F and G, right. So F offers -1, G offers -1, alright. So we have considered F, we have considered C, we have considered B, we have considered G, D is free. How about A? A I have arrested like what we have done here, we have arrested both rotation and vertical displacement at A, which means A offers -2. So let us total them, -1, -1, -1, -1, -2, total is 6. I have 6 degrees of freedom, constraints are 6, which means I am not left with any degree of freedom. Okay. So for the system, total degrees of freedom equals 0, which means it is a determinate system, alright. Which means what? I can use equations of equilibrium to solve it. Okay. Mind you, it's this way of doing should be done with caution. There are certain problems you will face, but I am not talking about it right now. For example, if this support had been over here, it is a completely different story. Okay. I am not going to talk about it in this particular problem. Okay. For now this holds okay, and we have a 0 degree of freedom system, which means that it is a determinate system and I can solve for them. Okay. Mind you, I have to do this whole for each one of these separately, and each one of these should have the proper constraints, then only it is possible to state that it is a determinate system. Okay. I have just over simplified it and said that here. Okay. Now if it is a determinate system with a degree of freedom equal to 0, what do I know? I can't apply virtual work method directly. I have to release at least 1 degree of freedom in order to apply virtual work principle, alright. Well, what is asked is find the reactions at A, correct, which means what are the reactions here? There is a moment reaction and a vertical reaction, okay. I may probably opt to release one of them and do the problem, okay. So let us do that. Again in this exercise please remember it is possible that you can free both the rotation as well as the vertical constraint here, which means you can make it free and have 2 virtual displacements taking care of it, okay. So for now let us make it simple, we will convert this into a single degree of freedom system by releasing the vertical displacement, alright. If we do that I am going to draw this line diagram again. What do I have? I have a support over here, I have another support over here, I am just drawing those supports. At A I am releasing the vertical displacement, yet rotation is not possible, okay. This is at A. Okay. How many degrees of freedom does it have? DOF equals 1, which means if I specify one displacement, vertical displacement or rotation at any one of these points, I can find out the virtual displacement at any other point, okay. The only condition is what I have to impose is a kinematically admissible virtual displacement. For example, I cannot opt to make a rotation over here, I cannot say okay I will put a virtual rotation and find out. Please remember it has to be consistent with the support conditions as well as the notion of rigid body, okay. So kinematically admissible displacements is what I have to find out, means consistent with support conditions and the rigid body notion. Simple, as long as I maintain this it is kinematically admissible function. So what is the best thing I can do? I can probably opt to move this guy, okay. How will it look like? If I move this, the entire guy will move, entire AB will move, right. So let us just draw, it is easy to draw. This will remain horizontal, the reason is I am not allowing any rotation, it is only possible to move it this way. So I have moved it and let us say this displacement is delta, okay, delta A, but uniquely specified, so I am just going to call it as delta, okay. Okay. At this point what should happen? This will not allow movement, which means the only way possible is going along this, okay. So the point C has to move down like this, okay. Now at point C again this guy will not allow vertical movement, which means the only way possible is a displacement like this, very simple, okay. Geometrically if I draw it, it will make it simple for me, okay. The moment I know this I have solved the problem, okay. Now let me draw the active forces. Remember I have not drawn any active forces yet, having released the vertical displacement here I have to apply a vertical reaction. Let us say this is A y, okay. Again it's an option, I have used vertical this way. So let us just have a notion of what would be the reference. The reference is the initial, and let us say this is the y direction I am looking at. Okay. I need only one reference here. The reference could be the initial starting point of this. Okay. And therefore, the y displacement, virtual displacement that has occurred is in the positive y direction. Okay. What are the other active forces? So, let me draw these active forces in this, okay, and then also indicate the appropriate virtual displacements. There is a 5 kilonewton here and a 10 kilonewton here, that is all. Okay. So, I am going to apply that. There is a 5 kilonewton applied here, okay, and this is the virtual displacement. Okay. I am going to now represent this as delta E. Okay. I have to write delta E in terms of delta if I have to solve for this. Do I need to draw anything else? Only here. Here I have a vertical force acting like this equal to 10 kilonewton, and this is the virtual displacement delta D. Is this clear? Let me first write down the virtual equation and then get the relationship between these through KAD, kinematically admissible displacements. So, what does virtual work equation principle tell you? AY dotted with delta in the same direction. Here, since only one direction is existing, I just have to write times. So, times delta positive quantities plus 5 times delta E plus delta D is upward. Please remember, I should have put the direction of these displacements. 5 kilonewton upwards, delta E upwards. So, that is why 5 plus 5 times delta E. Here delta D is upwards, 10 is downwards. So, I have to have minus 10 times delta D, which is minus 10 delta D, okay, and this is equal to 0. Simple. Now, if I have to find out, if I find out delta E equals something times delta and delta D is equal to something else times delta, if I substitute over here, delta will separate out, I will get the equilibrium concerning AY phi 1 minus 10 and can solve it. Okay. It is as simple as that. We will come back to that after finding out the relationships between these. Okay. So, I am going to draw this again over there. Delta A okay. So, let us start from here. I know geometry is very simple, so I am just going to go fast. Delta A, delta B, if I have to find out, delta B is equal to delta A. Okay. We also have delta E in between, delta E is also equal to delta A. Okay. Delta E is in this direction, delta B is in this direction, alright. How about delta C? Since this is exactly in the middle, the amount of movement here will coincide with the movement over here, very simple. Please remember we are looking at small changes. I have just drawn in such a way that these changes are too big. Please remember the rotation is such that this displacement is small. So for all practical purposes I am not going to consider the horizontal displacement. So this is delta B, delta C will be not the same minus delta B. Okay, I am just going to be consistent with the directions. Okay, I will take upward to be positive, downward to be negative. Okay, again looking at this, delta D magnitude will be the same as delta C because this is at the middle, but sign change. So I will have delta D equals minus delta C, that is equal to minus of minus delta B, that is equal to delta B, and given that delta B is equal to delta A, this comes out to be delta A. Beautiful, simple. And therefore what I have here is upward direction delta D is equal to delta A. This is what I get. Upward motion is positive, so delta D happens to be delta A, delta E happens to be delta A. Do I need anything else? Over. Now I have to write down the equation. I come back here, what do I know about this? Delta E is equal to what times delta? 1 times delta. What is delta D in terms of delta A? It is 1 time delta A. Okay, remember positive equal to, this is positive, this is positive. Now it is very simple, I just have to take this to be delta, this to be delta, and I get the answer immediately. So I have AY plus 5 minus 10 times delta equals 0 implies AY equals 5 kilonewton. Alright. Now there is a doubt, let us see if we can clarify. Supposing I have a rigid body, let us say straight member like this, if I tell you that one single point is constrained from rotation, alright, can you tell me what is the rotation of any other point? Please remember, rotation of any other point is 0, which means if I constrain rotation of a single point of a rigid body, every point of the rigid body will be constrained from rotation. Okay, and that is a fact that we use in the previous section of the problem. So when we had something like this, in this beam problem, when we released only the y displacement and kept the constraint of rotation, we had something like this. Right, till B, right. So when it moved up, remember this particular point is prevented from rotation with respect to the fixed frame of reference. So when I move this up, this point cannot rotate. If one point of the rigid body cannot rotate, none of the points of this AB can rotate, and therefore it has to only go up like this till point B. That is the only possibility. Okay, and therefore we did this way, consistent with again those two assumptions of should be able to be consistent with the support conditions and the rigid body notion. Now I want to find out the support reaction. Okay. If I have to find out the support reaction, we have already found out the vertical reaction, we need to find out the moment reaction. How do I find out the moment reaction? Very simple, I will start with the same kind of notion. The total degrees of freedom for this is equal to 0. I have to release the rotational degree of freedom at A, which means it should be it should be possible for it to rotate about this particular point A, which means from a fixed, if I have to allow only rotation, it is very simple. All I have to do is convert it to a hinge and apply a moment. We need to find out this moment A. Okay. So, in this particular case I have let me just denote the points. I have one 5 kilonewton acting here, 10 kilonewton acting here. This cannot move, this cannot move, these two are pinned with each other. So, AB, BC and CD are pinned with each other. We already saw that in the previous example. Now, in order to find this out, what should I do? For the virtual work principle, MA into the rotation that has taken place at this particular point is the virtual work. Okay. So, let us say I provide a rotation here equal to theta A. Okay. So, that the virtual work, let me call it as delta theta A. For now, let us just assume that the virtual rotation itself is theta A, okay, just to avoid too many symbols. And if I am rotating like this, what should happen to B? B will start to move up, right. I am just using the simple geometry. So, let me draw with some other color. It would have moved by this. Okay. How do I find out the displacement at B? That is not very difficult. This rotation times the length will automatically give me the rotation. Once this point has moved to this, we are left with the similar concept that we used earlier. This point cannot move. The only way that this displacement can occur is by movement like this. Okay. So, this is the upward movement. Mind you, I am just using the upward movement here. This rotation is given counterclockwise. Okay. That is the given virtual displacement. Okay. In this particular case, virtual rotation. Okay. Consistent to this virtual displacement, I need to find out. This is an upward displacement delta B. This is a downward displacement delta C. Okay. And again, consistent to this, I should get this, which is delta D. Simple. Now, once I find out delta B, from that I will find out delta C, from that I will find out delta D. Okay. So, what I am going to do now is find out kinematically admissible virtual displacements, because now we know we have to do that in order to provide the displacements, virtual displacements at 5 kilonewton and 10 kilonewton, apart from the virtual rotation that is already given. All right. At E, the distance from that support A to E is 1 meter, right, and therefore, delta E, is it upward? The answer is yes. The delta E is equal to 1 meter times theta A, upward. Okay. What is delta B? Delta B equals 2 meters times theta A, again upward. Can I find out delta C in terms of delta B? Since it is at the center, it is very simple. Delta C equals minus delta B. Delta D is minus delta C, and that is equal to delta B. Okay, and what is delta B? It is equal to 2 times theta A. Do I know delta D in terms of theta A? The answer is yes. Do I know delta E in terms of theta A? Yes. Now I am ready for writing the virtual work principle. So the virtual work principle now is MA times theta A. So MA times theta A. Remember the direction of MA is counterclockwise, theta is also the rotation in counterclockwise direction. So this is a positive quantity plus 5 kilonewtons times delta E is equal to theta A times 1. How about this? This is a positive delta D but a negative this thing, so it is minus 10 times what is delta D, it is 2 theta A, so it is 2 times theta A and that is equal to 0. Okay. Separating theta A, I have MA plus 5 minus 20 which is minus 15 equals 0 or MA equals 15 kilonewton meter. Okay. Why is it so? Because theta A cannot be 0, it is arbitrary. If it is 0, it does not make any sense, and therefore MA should be equal to 15 in order to satisfy this equation. That is it. Okay. One of the advantages of this is if kinematically admissible displacements are easy to find out, nothing can beat virtual work displacement method. Okay. Now as I said earlier, it is possible to do vice versa. Supposing I need to find out kinematically admissible displacements from a set of equilibrium forces, it is possible to find out. Okay. We will take up that example in the next module. Any questions? Is this clear? Now as an exercise, I want you to apply both the virtual displacements, vertical and rotational, and then consider what is going to happen. I will give you a clue. The first thing that you have to do is at this point A, if this is stuff, this is B, this is C, what have I released? I have released the support completely. I will have AY and the moment MA acting on this. There will be this active force at the middle equal to 5 kilonewton, here 10 kilonewton. I have these supports still present. This is the body for which I need to find out. What should I apply? I should apply a vertical displacement and a rotation. If I do that, then I will be able to find out. So what will happen? I can apply vertical displacement and a rotation, which means I will be applying like this, mind you. Okay. So this is the rotation theta A, this is the displacement delta A, and find out consistent to this. So you know how to find out this, from which you will find out this, from which you will find out this. Okay. Mind you, it will be in terms of delta D and delta E will be in terms of delta A and theta A. Separate the expressions, each of the coefficients of the expressions in terms of delta A and theta A should be equal to 0. You will get the two equations simultaneously. You can solve for that. I will leave this exercise as a homework for you. Thank you.